Okay, welcome back to our Chapter 2 test review. This is our practice test, and I'm beginning on the third page. So we have been, is that right? Yep, we're beginning on the third page, and starting with number 5. So we are to, as you can see, graph the function, list end behavior, asymptote, vertical asymptotes, x and y intercepts. But again, the test will be formatted in such a way you really shouldn't forget any of those aspects to it. Okay, we are not looking necessarily for the most exact graph, so we won't have to t-chart, 20 points or anything like that, but we do want to have a real good feel for the kind of global behavior of this graph. So first thing I want to do, I want talk about my 3 zero tests. So I'm going to let the numerator equal 0, and when the numerator equals 0, I have 2x squared minus 8 equals 0, or if I solve for x, I get x equals, I would add 8, divide 2, get 4, take the plus or minus square root, so plus or minus 2. Now we could have gotten that just as easily by factoring this. If I factor out a 2, I get 2 times x squared minus 4, and then I can quickly see that I have factors of x plus 2, x minus 2, yielding these. Okay, denominator equals 0. Well, that denominator factors into x minus 6 times x plus 1. Let's check it. X squared plus an x minus 6 x's and a minus 6. Therefore, the denominator is 0 when x equals 6 or negative 1. But really, the denominator can't equal 0. What I do notice is we do not have a hole in this graph because I don't have the same zeros on top as I do on the bottom. And my last test is just let x equal 0. I'm going to put that over here. X equals 0. And the only reason I do that, as I mentioned before, is because it's just such a simple value. I put in 0 for x, and I get negative 8 in the numerator, negative 6 in the denominator. I get 4/3. That's just usually the easiest ordered pair to get that fits on the graph. So let's see what we have. When the numerator is 0, the function is 0. So when I put 2 in, since the denominator is not 0 and the numerator is, I get 0 divided by something, I get 0. So I get a point at 2, 0. Likewise, I get a point at negative 2, 0. Those are our x-intercepts. That would be 2, 0 and negative 2, 0. Y-intercept occurs when x is 0. I have a y-intercept at 0, 4/3. And denominator, it can't equal 0 at 6, or excuse me, the denominator can't equal 0, so x cannot be 6. 2, 4, 6. Since that's not a 0, that doesn't cause problems in the top, I don't have the matching factor at the top, we expect an asymptote, vertical, and a vertical asymptote at negative 1. So my vertical asymptotes occur at x equals 6, negative 1. Now I wrote that up here as not equal to, but the equation of the asymptote is equal to. X equals, in fact, I probably shouldn't be that lazy. I probably should say x equals negative 1 and make a proper line out of it. End model asymptote. The end model asymptote is what I refer to as the big X test. It's what our limits are as x approaches infinity. And as x approaches infinity from the positive side, the 8 becomes insignificant, the 5x minus 6 becomes insignificant, and it wants to look like 2x squared on x squared. X squareds cancel. This graph just eventually wants to look like 2. So it wants to look like, I don't know why I'm using blue here, it wants to look like y equals 2 to the right, and it doesn't matter if I have a negative in here. It's still positive divided by positive. It's still x squareds cancel. Insignificant, less significant, I should say, values as x gets big. So that is our end model asymptote. So our end model asymptote is right here. I want to go back, talk about these x-intercepts. That's my That's my avenues for my mole men to get up to the top. That's my little potholes, or my little manhole covers right here and here. That's the only place we can cross through to get to the top. So, maybe somewhat surprising, it appears as though we're going to pass through this asymptote right here. Well, let's take a look. You say, well, how can I go through that asymptote? Don't I get sucked into asymptotes? Well, that asymptote exists when x is big. Remember, we got that from the big X test. X is not big around 0. So this, ultimately, we would get pulled into this asymptote out to the extreme right, extreme left. Now, might this just hit this 0 and curve back up then and look kind of like a parabola? I know I can't go under and come back up. Well, that 0 came from a factor. Here's my numerator factors, x plus 2, x minus 2, came from a linear factor right here. So it's going to pass through that like a line. Now, I don't know how low it stays here, but it can't cross back above 0 again. So this middle graph looks sort of like a cubic. It is not a cubic. Cubics aren't asymptotal, but it has that kind of feel, kind of a little bit like a tangent, part of actually a cotangent curve or a negative tangent curve. Okay, so what's happening in here? Well, this is not a touch point. This is a 0. This is just a single 0 from right here. So I must pass through there. And now's where I expect. Now, is it possible that we might come up here and cross this asymptote? It's possible, but I know eventually I'm getting pulled into it. We might be able to cross that asymptote and get pulled in. So maybe we need to investigate some more x and y values. But again, we were just talking about a nice global representation of this curve. Okay, so now I've got to talk about region A or B. A up here, B down there. And it should be clear where we are. If I was in B, I would need a manhole cover to get through here. So I must be in A and get sucked into here. Now, as I said, there's a good chance maybe that curve gets pulled in a lot closer here. Maybe it's farther out here, but that's a good global representation of what our curve looks like. Kind of an interesting one, passing through that asymptote. There you go, man. Okay, next. I've got another function here. I'm going to go ahead and see if I can factor the bottom. Are there factors of -6 that add up to 5? Yes, there are. So this factors, and you can check me on this. This is 2x minus 1 times x plus 3. That gives me 2x squared plus 6x minus x plus 5x and a minus 3. So therefore, my numerator is 0. Let's start with our numerator test. X minus 3 equals 0 produces x equals 3. We'll move on to there. We'll move on to there with our denominator test. Set our denominator equal to 0 because we know our denominator cannot be 0. Therefore, our denominator, x cannot equal, add 1, divide 2. X cannot equal, subtract 3, those values. And once again, what do we notice? We don't have shared zeros in the top and bottom. So there is no hole, so that tells us where some asymptotes are. It tells us where a point is. And finally, my small mini t-chart. If x is 0, I get -3 over, if x is 0, -3 for a point of 0, 1. So what do I know? The numerator is 0 at 3. So when I put in 3, I get a numerator of 0. 3 is a 0. That's an x-intercept. Y-intercept, 0, 1. Vertical asymptote at 1/2. X cannot be 1/2, and x cannot be -3. So let's go with our big X test. When x gets huge, this wants to be, the negative 3 doesn't matter much, the 5x doesn't matter, the negative 3 doesn't matter much, and I get x on 2x squared, which wants to look like 1 on 2x, and as x gets huge, I get 1 divided by a billion. As x gets big, I'm getting pulled into 0. My horizontal asymptote, my end model behavior, is y equals 0. Once again, we're on an asymptote here. How about what's going on here? Oh, vertical asymptotes, didn't write those down yet. We've got x equals 1/2 is a vertical asymptote, and x equals -3 is a vertical asymptote. How about what's going on in here? Can this come down, touch this, and then continue like the graph above? Or must it go up? Well, I can't hit 0. Remember, my only 0 on this, my only passage for Mole Man is to be down here, come up here. If I'm up here, the only way I can get down there is to go through here, but I'm not going to get there going through that asymptote. So, I don't know where the low point is. And maybe you want to add to the t-chart. Maybe you want to put in -1, -2, and see how low this goes. But who knows where the lowest point is? I suspect it probably comes down something along that line and then hugs into that asymptote. But it definitely does not cross there. So, let's find out where we are over here, A or B. In the big X test, there's a little more to be learned. As X approaches infinity, positive infinity, let's think about this. If I put a billion in here, I get a billion over 2 times a billion times a billion. These others don't matter much. The billions cancel, and I get 1 over 2 times a billion, which is virtually 0, but it's positive over positive. Positive over positive, approaching 0 means we are up here. Now, here's the big question. How high up do I go? So again, if I wanted to know how high up I went, maybe I'd put in 1, 2, 3, 4, 5, or something like that. But I suspect maybe something like this. Maybe not that high. Maybe it comes quite a bit higher. But again, we have a nice global representation. We know we're over. Does it bounce here at this single 0? Nope, it acts like a line and heads down. You might want to fortify that. You might want to say, let's put in 4 here and see what happens. Real easy to do. We just put in 4 here. Okay, how about over here, negative infinity? If I put a huge negative number in here for x, I get negative over a much huger positive. Negative divided by positive is negative, but again, approaching 0. We have to be in here. And I have no passage out of there. Therefore, this portion of the graph has to look like this. And we have enough information there to answer all of our interesting calculus questions, like what's the limit as we approach 1/2 from the left, infinity? What's the limit as we approach 1/2 from the right, negative infinity? I don't necessarily know how close I get over here or how far away I get, but we have all of our little interesting calculus type questions. Okay, hope global representation makes some sense to you. Let's take a look at C. Here we've got, this could be x plus 1 times x minus 1 on x minus 2. Again, no holes in the graph. Surprising we haven't had one yet. So, numerator test. When's the numerator equal to 0? When x equals -1 or positive 1. What's that mean? -1 makes the numerator 0. Positive 1 makes the numerator 0. Those are our only x-intercepts, and they're single zeros. We just pass through. Y-intercept. So let's continue with this before we get to y-intercept. Denominator equals 0. Oh, well that's when x equals 2. But x cannot, the denominator cannot be 0. So x equals 2, that doesn't match numerator, so it's not a hole. There's a vertical asymptote at x equals 2. Okay. Well, it's shaping up kind of like an interesting graph. How about one more easy point? X, y, let's put in 0 for x, and I get -1 on -2, I get 1/2. So at 0, I'm up at a half. Okay. Next is the big X test. We got some explaining to do in here what's going on, but the big X test might clear it up. I've got a second degree equation divided by a first degree equation. That wants to be a first degree equation. In fact, it wants to be a first degree equation with slope 1, because x squared on x is 1x. However, it might be, so I have slope 1, it might be up or down. My temptation is to say it appears as though, if this is slope 1, it appears like maybe I've got an asymptote up here. That would kind of fit with those 3 points I have. I don't know. Maybe it's down, maybe I'll be surprised. But how do we find that out? We long divide. So I'm going to use this space over here to take x minus 2 into x squared plus 0 x's minus 1. Let's see what we get there. X goes into x squared. X, we knew that, giving me x squared minus 2x. What do I do there? I subtract these values, and I get plus 2x minus 1, and x goes into this 2 times. And whatever remainder I have doesn't matter as far as my end model behavior. This graph wants to look like y equals x plus 2. Let's see what that does for us. Puts a point, y equals x plus 2 right here with slope 1. We're going right up through here with our slant asymptote. Slope 1, oh look, it was just kind of what we thought it might be. So I believe this curve, and it has to be because it has to pass back through here. Does that mean this is the highest point? No, not necessarily. It may get higher up here or higher over here, but global representation, we're getting sucked into this asymptote. We have our y-intercept. I've already got that one. That was, where are we at there? That was 0, 1/2. And now I have to decide, is my graph up here in A or is it over here in B? And I'm going to say, I know where it is. Now believe me, we can have functions that look like this, both going down, kind of a bottomless pit down here, volcano, bottomless pit. But we exist up here. I want you to think about that for just a second. Why do I know we exist up here? Hopefully you said no manhole cover, no other 0 down here. I can't exist in here. I'd have to pass through either a hole in the graph or a 0, and we don't have either of those. So once again, we've got our end model asymptote, we've got all of our points, we've got our interesting calculus questions. What's the limit of this function as x approaches 2 from the left? Negative infinity. From the right, positive infinity. What's the limit as that function approaches infinity? Infinity. Negative infinity, negative infinity, and discontinuity, infinite discontinuity at 2. The graph has all the answers for us. Okay, find the limits by the method of your choice. It's going to be find the limits by hand by the method of your choice in this section right now. We're not going to go ahead and do that with graphing. We may look at some to graph in the future, but we don't need to on these. We do know when we see this, when we have sine of x, I want sine of x on x. I could actually multiply top and bottom of this by 1 on x and just be completely driven by this sine of x. But sine of x is on x if I rewrite this as limit as x approaches 0. I could make this 2x on x plus sine of x on x. And 2x on x is just 2. Limit as x approaches 0 of 2 plus sine of x on x. But what is the limit of 2? 2 is just 2. So this is 2 plus what is the limit as x approaches 0 of this? That's our only trick in limits with trig functions. That is 1 for a total of 3. You see sine of x, you make it be on x in a limit. Okay, what's the limit as we approach negative infinity? This wants to look, follow this. This end model behavior, x to the 4th dominates x to the 3rd. Doesn't seem like it would, but by the time we get to 1 billion, it's 1 billion times bigger than that. Because this is 1 billion times 1 billion times 1 billion times 1 billion, and this is 1 billion times 1 billion times 1 billion. So this thing dominates that. So when x gets enormous, the x cubed doesn't have a big effect on it. 12x cubed. So I end up with x to the 4th on 12x cubed, which wants to look like x on 12. Right? X cubed reduces. Now, it wants to look at like x on 12, and I could go ahead and long divide and figure out, like the problem above, is it 1/12 x plus or minus something? Well, either way, if it's 1/12 x, this graph ultimately is going to have a positive slope of 1/12. This is if it's up a little bit. But no matter where it is with a slope of 1/12, the further I go to the right, the higher I get. The further I go to the left, the lower I get. Therefore, the limit to negative infinity is going out this way. It's going to continue down forever, is negative infinity. Now, when I said not going to do it with a graph earlier, I realized I just graphed this, but that's graphical analysis. That's not graphical calculator. Okay. Limit as x approaches 2 from the left. Here's where people get hung up. They think about the entire graph. What does the graph look like? And you know what I really care about here? I really care about what this graph looks like at 1.99999. Nothing magical about me choosing 5 decimal places here. But you get it? I want to know what's happening when x is really, really close to 2, but just a little bit left of it. If I put 1.99999 in here, I get 0.00001. And 1 on 0.00001 is what? 100,000? So this is going to get bigger and bigger and bigger the closer I get to 2 from the left. However, it's going to be negative. 1.999 minus 2 is actually negative 0.00001. Therefore, I got a positive over a tiny, tiny, tiny little negative. It's going to approach negative infinity. Is that okay? Basically, yeah, 1's not big, but relatively, I'm going to have big positive over little negative as I get closer and closer and closer to 2 coming from the left. So big positive over little negative approaches infinity, but positive divided by negative is negative. Whereas, I don't care about the whole graph, I care about what happens here. When I put that in, I get 0.00001, and I think 1 on that, you can check me on this, is 100,000. But it's a positive divided by positive approaching infinity. This one is positive infinity. All right. We will pick it up from here, from number 7, on the next video. Thanks for checking in.